Okay, so before we discuss the solution to the two problems that I sent in your portal, let's first recall what we've been talking about already before the suspension of classes. So we were discussing the different types of DC generators according to the connection of the field windings. So I hope you can recall that we initially have two main types. The first type is that wherein your field is actually being supplied by a separate source. So if you're going to draw now the diagram of the first type, it's called your separately excited generator. Separately excited. And as you may have recalled already, you need current to pass through your field in order for you to produce your flux. And that flux is going to be cut by the rotating conductors to produce an EMF, which is here. This is your generated EMF. And your armature is, of course, resistive, so it has an armature resistance. However, the field is not connected with the armature, so it's separately excited. The next types are your self-excited generators, and they're divided into four. So for your self-excited, it all depends now on the connection of your field winding. So you can connect your field winding in series with your armature. So it can look like this. Your field, again, it has a resistance, so we will call that RSE. Armature resistance is RA. Remember that if you're going to connect your field in series with your armature, it must be of low resistance. Hence, in construction, again, recalling the series field resistance usually is made up of thick, heavy wires with few turns. And if you're going to analyze that few turns, heavy wires, that means short length and large cross-sectional area, so very low resistance. Why? Again, because you are connecting the resistance in series with the armature. I hope you can recall those discussions. You can also connect the field in parallel with the armature. So here can now look like that one. So this is now your field, and again it has a resistance which we called RSH. And again, the nature of that being, if you connect a resistance in parallel, it should be high so that its effect is going to be negligible. It should be high in value, and you can of course attain a high value of resistance if your length is long and your cross-sectional area is small, or if the conductor is thin. So these field windings are usually fine wires of many turns. The last two types for this self-excited generators are your compound generator. So this is the series. This is shunt. Again, I've discussed these already, but we're just doing a recall before I do the examples. So the compound generator has two types. It is making use of both the series field and the shunt field windings. So the first type is, or has this diagram wherein you have the series field here outside going to the output, and this is the location of your shunt field. This is your short shunt compound gen, and the last type, of course, is your long shunt. The only difference is the location now of your series field. For the long shunt, the series field is located here. And then, of course, you have your shunt field, which is here. So series field there. So this is now your long shunt compound generator. All those four are your self-excited generators. And of course, again, it's just a recall. I'm just concerned with probably other students might have left their notes before the suspension. So this is what we were discussing. And of course, you have other parameters here, such as if you're being asked of the terminal voltage, it's the voltage across these two terminals where you will now tap your load. And then you also have your line current or your load current, which is here. You have your field currents passing through the field. It depends upon which field. If it's passing through the series field, then you have there your series field current, of course. If it's passing through the shunt field, you have your shunt field current. And you also have the current passing through the armature, which we labeled RA. And another thing to take note is the direction of current. It should be coming from the positive terminal of your EG, and everything else is going to follow from there. So we will not be writing all the equations anymore because that's going to be pointless. We did that already in the classroom, and secondly, there is no point in memorizing those equations. It should be that you should be able to write those equations already, making use of the network laws and theorems you've learned from your previous electrical engineering course. Simple KVL and KCL equations are going to be fine. So those are basically the only two theorems you need to analyze different types of DC generator. So let's try for the first problem. So for the first problem, it states the field current of a 100 kilowatt 250 volt shunt generator is 5 amperes when delivering power at rated terminal voltage and rated load current. The armature resistance is 0.01 ohms. Determine the generated EMF and the efficiency of the generator. So right off the bat, you are being introduced with two values here, 100 kilowatts and 250 volts. So the first thing you should understand is when the problem is stated like this, these are actually your nameplate ratings, the 100 kilowatts and the 250 volts. You call them your nameplate ratings. And the nameplate ratings for a DC generator is always, for the power, that's always your output power. So it's 100 kilowatts and the nameplate rating, which is the voltage, is always your terminal voltage. So terminal voltage being 250 volts. It's a shunt gen, and we're looking to solve for the generated EMF and the efficiency. So if we're going to draw a shunt generator along with the values, so we're going to be labeling the components. This is unknown. Generated EMF is unknown. This is your armature resistance, which is given to be 0.01. Next, you also must be given the field resistance, I suppose. Or no, it did not give the field resistance. So that is also an unknown. However, we were given that it's the field current of a 100 kilowatt 250 volt shunt generator is 5 amperes. So we were given that this field is taking in 5 amperes. The direction must be downwards. So remember, current will come from the positive terminal. So it will go to that direction. This being your armature current IA, the current passing through the armature. And then at this node is going to divide into two. One is going to your field, the other one is now going to your load. We were also told that it's delivering power at rated terminal voltage and rated load current. So what does that mean? It means that if you are supplying a load of rated values, it means that that load has a power consumption equal to the nameplate rating of the generator. So it says at rated voltage, so it's 250. So the rating of the terminals of the gen is 250. So this is 250. And it also says at rated current. So what does that mean? The current passing through your load, IL, is computed based on the fact that this load is running at a power of 100,000 watts. It's running at full load. So if it's running at rated current, it's running at full load. So it's consuming all the 100,000 watts available that the generator is allowed to supply. So we will be starting with the analysis at this portion of the circuit. However, let's first try to recall what we need. We need the generated EMF. So how do you solve for the generated EMF? We can solve for the generated EMF if we do KVL at this loop. And we can only do KVL at that loop if we know the voltage here. At the 0.01 voltage drop at the armature, 0.01 ohms. So what is the voltage across that resistive element? And we can only solve for that voltage if we know IA. So everything will fall into place if we can determine first here IL, which we are going to do now. So what is IL? So IL, Again, that's your rated current based on the nameplate rating, which is a value of power of the load. Power is voltage times current. So from there, your rated current can now be solved by dividing power to the voltage with the voltage. So this is 100,000 watts divided by the power, which is 250. And that must give you 4 times 100 is 400. This must give you 400 amperes. There. So since IL is 400, we can now look at this node. This one. Let me say that is node X. Why am I labeling that X? Because we know IL, we know that this is 5. We can solve IA from there using KCL. Okay? KCL states that currents entering a node is equal to the currents leaving that same node. What are the currents entering the node? So we only have one current entering the node. It's IA. What are the currents leaving that node? We have 5 and IL. IL is said to be 400. So we're going to substitute that already to determine IA. IA therefore is 405 amperes. There. So that is our armature current. Now, since that is our armature current, you take a look at this loop because I suggest we can now perform a KVL at this loop. So let me call that loop A. But before we do our KVL, let us be clear on our voltage drops. So again, for passive elements, I taught you this already. So for this direction, it will enter the positive terminal and leave the negative terminal. Only for passive elements, because it's the other way around for sources. For sources, current is going to leave the positive terminal, enter the negative terminal. For passive elements, current is going to enter the positive terminal and leave the negative terminal. So if we do this loop, we also have that same direction here, plus, minus, there, because the current here is downwards. We need that for the exit polarity rule for our KVL. However, if we're thinking of solving the voltage here, it must be, you might be thinking that we should need also the value of RSH, because the voltage here is 5 times the value of RSH, right? Current times resistance. However, you should remember also that this voltage is the same as this voltage. They are the same potential. This point is the same as that point. This point is the same as that point. The voltage here is 250. Therefore, the voltage here is also 250 ohms. Volts, rather. Sorry. So there, I guess we're now ready to do our KVL equation. So KVL, we go clockwise at loop A. Sorry, the column must be there. Okay, exit polarity. So if we go clockwise, we will exit at the positive terminal. Voltage there is EG. Next, going clockwise, we will exit at the negative terminal here. Voltage there is current times resistance, right? Current times resistance. So current is 405, resistance is zero point zero 0.01. And then last, for this component, we will exit the negative terminal, so minus. Voltage here is already given, 250. So algebraic sum of all voltage rises and voltage drops across a closed continuous loop is 0. So from there, we now have a value for EG, which is equal to 250 plus 4.05, which is 254.05. So that's the voltage. Lastly, we also need the efficiency. So what is the efficiency here? The output efficiency is always the ratio of output power to input. Let me just allot a space here because I have no more space. So efficiency is always whatever you're solving for, it's always the ratio of output power to input power. The only thing to settle would be what is the output power. Of course, for this one, it's running at an output of 100,000 watts. So you know that already. What is the input power? Now, if we look at the totality of the system, the input to the generator must be a mechanical power because it's the one that is going to produce the necessary rotation. However, we do not have the means for solving the mechanical power input here. So if we're going to trace the power flow in this system, you have a motor which is making the generator rotate. So it has an input, it has losses. After the losses, you will be able to produce here your electrical energy. And the electrical energy is something that we can compute. So there is no way for us to be able to compute for the mechanical energy because we do not know the losses here. The losses between the generated EMF and the mechanical power is usually called your stray power loss, which is not given in the problem. So the input we are supposed to consider is not the mechanical power, rather it's the generated power. So from the generated power, you will have losses here again, electrical losses this time, before it becomes now your final output. So the input we can consider is the generated power. What is the generated power? It's the product of, we've discussed this, it's the product of the generated EMF, which is 254.05, and the armature current, which happens to be 405. Okay. That will, of course, give us, if we want it in percent, we can multiply it by 100%. So solving for the efficiency, 254.05 multiplied to 405, 100,000 divided by answer. The efficiency is 97.19%. This is not the efficiency of the genset. It's only the electrical efficiency of the system. The input is the generated power, the output is the nameplate rating, 100,000 watts.